All right. We can begin. Thank you all for coming, and let us just jump into our work that we left last time. So last time we saw null space. Let me just quickly go through the slides so you can remember. So last time we noticed that we can call all vectors that A sends to 0 as null space. Then we recognize that it can be a orthogonal basis in the null space can be computed by a single operation in major languages. It is based on SVD decomposition. Then we recognize that any vector in the null space can be represented by a coordinates in this basis, basically the way expression 1 is written. And then I proposed a way to call something orthogonal to a linear subspace. That was by saying that you are orthogonal to the subspace. The point is orthogonal to the subspace if the closest point to it is an origin in the subspace. Okay. So if a point is orthogonal to the subspace, if non-leaf, the closest point to it in Euclidean metric is 0 point. Then orthogonal space orthogonal to a given subspace is a space of all points that are orthogonal to it, and together they form the whole space. Okay. We also define projection. Projection is the of point X onto subspace L. This let's just put it in simple terms, right? If you have a point X, that its projection to subspace is the closest point on the subspace to it. And if you want to project this point to orthogonal subspace, you do it the same way. You just find the space. If you have a point, you find the closest point on this orthogonal subspace to it, and that is the projection. So, and projector is given as expression number 2, as a projector matrix. All right. And what we managed to do is to say, okay, let's say we have vector A, its projection onto subspace L is given as expression 2. So its projection onto the subspace orthogonal to L would be given by expression number 4. Why? Expression number 3 showed us how. So we basically obtained 2 projectors. Those was the results from the last lecture. Okay, now we can move on to row space. I hope all of this was trivial, but maybe except for the clarity of definitions. The ideas, I think, were trivial, right? You do need to, remember expression number 4, expression number 2, though. That is already something required of you to remember. Okay, good. Now let's go to row space. What is a row space? Well, definition that I proposed here is row space is just orthogonal complement of the null space. We just defined what orthogonal complement is. It is a space of all points which are orthogonal to the subspace. So we can use the definition to just define a row space as orthogonal complement. It is a constructive definition. It seems like a just, it seems like just a definition that would serve, my laziness, right? Very simple to say, very little to give you. But it is a constructive one. Why is it constructive? Because saying that row space is orthogonal to null space already allows us to use 2 tools that we know. First tool is, if we know a projector onto the null space, we can automatically get a projector onto the row space. How? Let me write it down for you. I'll write here this time, and the camera points in this direction, so we will see. Let's say P is a projector onto the null space. Okay. So let's say for vector A, its projection onto the null space would be given as an equal to PA. And we know how P can be constructed. P can be constructed as N transpose, where N is a null space for some linear operator, a null space basis. Okay, so let's say we have this. Now we can automatically project onto the row space using this operator I minus P, because why? Why so? Can someone tell me why? Why the expression that I've written on the blackboard is valid? Just from the fact that row space is orthogonal to the null space. Tell me why? Row space part? Why? Why does it consist of two parts?
Because they are orthogonal to each other, and it will have like a magnitude of one, like the combination, the total.
Yeah. What we can say is, if we have the sum of two subspaces, the linear space and its orthogonal complement, gives us the entire space. This spans the entire space. Why? It follows from the definition of a orthogonal subspace. How does it follow from definition? But we said that orthogonal complement of a subspace is a set of all points which are orthogonal to the space. So let me put it this way. If you have a plane in the 3D space, its orthogonal complement is a line that goes through the origin. This is the origin. Okay. Together they span the whole space. If it was a 4-dimensional space, it would be a 4-dimensional plane here. By definition, orthogonal complement is everything that is not in the subspace. And together they have to span the whole space. Okay, now, if we have a basis in this linear subspace L, and we have a basis in this orthogonal subspace L perp. Perp is, by the way, denoted by something that looks like a mirror image of a transpose. Okay, a mirror as in like symmetrical image. Okay, so we have two bases, and together they span the whole space. Then the basis of, let me write it, basis of L combined with the basis of L perp would form a basis in the ambient space. That has to be true. If it wasn't true, if there existed a vector which is not a linear combination of those two, it means it is not in the linear space. Okay, so it's let's say it's purely not here. If there is okay, let me make the argument just for the sake so you can see the way I argue those things. Let's say we have a vector A, and it is not in linear combination of those basis elements. Okay, what that means? It means that we can represent A as an element that is spanned by those this basis plus A which is purely perpendicular to all of those guys. Okay. Yes. Sorry, come again. Yeah, I know. Sorry. The row. Oh, okay. Thank you so much. That is, I think, fixable. Let me just try to do it. Thank you. I will put a line here so I can see. Thank you so much. So imagine that this guy, so this guy is spanned by linear combination of those columns. This guy cannot be represented. I mean, the closest vector to this guy in those in the span of those columns is 0 vector. Okay, we can always decompose any vector in this way, right? We can decompose a vector as a linear combination of a matrix columns and everything left. And everything left will have the closest vector to it in the span of the guy as a 0 vector. Makes sense, right? Does it make intuitive sense or doesn't? Does it not? I think it's something you need to sleep on. Like imagine you have a three-dimensional basis, right? You have a plane like this that goes through the origin. Let's say origin is here, for example, like at some point. I'm sorry about the, let me try to make the argument while I was standing from the camera. So imagine you have a plane and you have an origin. The plane goes through the origin. You have a point here somewhere, just randomly. You can always represent this point as two components. One component that goes along the plane, and one component is perpendicular to the plane, but it's of course going through the origin. That is true for any dimensional space. It's the whole story is just very simple. You have a part of the vector that can be represented by a linear combination of the spanning vectors of the subspace. Everything else, if you put if you make this everything else orthogonal to your subspace, the closest vector to it in the subspace is going to be 0 by definition. So, and you can always do it this way. Okay, does it make sense? So basically, I'm saying that A can be decomposed in this way. If A lies in the span of this guy, the perpendicular component will be 0. Okay, let's say it is not 0. So assume that it is not 0. Then basically what we said that is the combination of those two guys does not span the entire space. So there is a vector that is not, basically that they don't span some subspace of the entire space. That contradicts the definition because this other element, it will be, let me check. Can I write here? Well, I will write here. Let's say that there is this additional subspace element, which is together with those will span the entire space. It will be perpendicular to both this guy and this guy, right? By definition of this guy, it is all vectors that are perpendicular to those to the subspace. So V has to be included here. So this is how we can argue through this, nonsense. Sorry if I'm covering part of the Blackboard for you. You understand, right? There is not a lot of meaning in this argument. It's it's very simple to make. Basically, you could have made it probably in half a line. But I'm just trying to give you a way to, you can go through it slowly and surely. Okay, good. Now, so with this guy, coming back to it, do we have an eraser? Okay, with this guy, what you can say is A would have to be equal to some two components, AN and everything else, AR. We'll just call it everything else for now, okay? AN, we know that it is given as PA plus AR. So AR is then given as identity minus P times A, because you put this guy here with a minus sign, you have an identity here. That's how you derive this formula. Make sense? So that is all we need to say. And now, we know that this guy would have to be in the subspace, which is not the null space, because if it was in the null space, it would have landed here, because this is a projection. This is a projection operator. Projection would put everything that is, every component of A, which is in the subspace, N, would go here. It cannot leave anything behind. That is the definition of a projector. And since it, everything is behind, cannot be in the null space. So Rn would have to be perpendicular to Rn. Sorry about the garbled Blackboard. It's pretty difficult to write this way. My apologies. Okay, I will erase part of it. All right, so this was why it is a constructive definition, because if you know that Rn is equal to PR, then you know that R is equal to I minus PR. That is the reason. So this is why it is constructive. If you know that row space is a complement of the null space, you can immediately use it. Now, second one, row space is also a space of all inputs of matrix A, which produces non-zero outputs, unique non-zero outputs. I think it is clear what I mean, except for one word, unique. I don't think it is included here, the word unique in this definition, which is a omission, but a space of all inputs that produce unique outputs. That, by the way, would also be a pretty bad definition, I would say, overall. So I would much prefer the first definition. But you can think about it as the correct definition will be go as follows. Row space is a space of all inputs, smallest norm inputs that produce unique outputs. That would be the good definition. But you can see now we have to unpack unique, smallest norm, and non-zero outputs is, I hope, clear. So what do we mean by unique? Well, what we mean is you give me one input from the row space, and I give you one input from the output space of the matrix. You give me another element, I will give you different output. I cannot give you the same output for two inputs. That is definition of unique. And smallest norm is you give me input from the row space, I give you an output from the output space. And for this output, you cannot find any vector in the ambient space which would have a smaller norm, which would produce the same output. Let's unpack it. I will see if I have a next slide unpacking it. No, I don't. So let me try to unpack it on the Blackboard. Okay. Let me put this. I suspect that we will have the same argument on the slides soon, but let's just go through it on the Blackboard. Imagine you have an input X to the matrix A, and it is in the row space. You'll have output Y. Makes sense so far, right? Okay, just definition. Now imagine you have input X and input XR and a plus XN, where X, let me just write it here, XR is in the row space of A, and XR is in the null space of A. This would also give me Y. Is that correct? Is it clear? Because XR plus A XN, we just open the brackets and this guy has to be 0 by definition of null space, right? Okay, good. So what can we gather from it? First of all, we can gather that this particular output will be produced by any XN, but only for a single XR. Okay. Why only for a single? Okay. Why for any XN? Because of this argument. Okay. So we have entire subspace mapped into a single point. Would this guy be the smallest norm guy that would produce Y? Well, it would be. Why? Because norm of XR plus XN will have to be bigger than the norm of XR because XR is perpendicular to XN, the orthogonal. And by Pythagorean theorem or whatever the name of the theorem you would want to invoke, sum of orthogonal vectors will have to be bigger than the norm of the sum would have to be bigger than the norm of components. Okay? For orthogonal vectors. That is clearly true, right? You know, imagine you have a vector of this length, a vector of this length, their sum is going to be bigger than any of the components. If they were not orthogonal, could have been different, but they are orthogonal. If they're not orthogonal, you could add to this vector, and the sum is actually smaller. But that is only for not orthogonal vectors. Okay, good. So this is the smallest value. But why is it unique? Let me put it this way. Why cannot I find another XR such that would produce me Y again? let's prove this as well. Where can I prove it? Hopefully here. Imagine you have a xr1, sorry, xr1 equal to y equal to a xr2. Well, what it means is xr1 minus xr2 would be equal to 0, correct? That means that the difference in, between those two values would be equal to, would lie in the null space of A, correct? And by definition of linear spaces is any linear combination of elements of the space lies in the same space. So this is contradiction. So this is impossible. If both of those are in the row space, their difference is also in the row space, but we showed it was in the null space. So this proves uniqueness. So this was the way to prove smallest norm. This was the way to prove uniqueness. Good. So those two definitions are kind of like equivalent, but the first definition I feel like is slightly easier to use. Good. Now we can see here expression number 5 is our projector onto the row space. Okay, this is the projector onto the. Wait. Okay, sorry, should read my own slides. Now, let us try to find the conditions for when the vector is in some space. So we have vector x, and we have matrix A and the null space basis n. And we want to check if x is in the null space of A. Well, what does it mean to be in the null space of A? It means that the projection onto the row space is 0, correct? Well, this is the projection onto the row space, expression number 5, and it should be 0. So this is a condition, basically. Expression number 5 is a condition that the x will be in the null space. Looks strange, maybe a little bit, but is also, perfectly usable. Now, condition that the vectors in the row space is expression number 6, just to project it into null space and prove that it is 0. Can someone tell me a different way and simpler computationally how to check the same thing? How to check that the vector is in the null space easier without like than expression number 5? Come on, the obvious question. How to check that the vector x is in the null space of A? A? Yeah, multiply x by A and see if it is 0. If A times x is 0, it is in the null space. So you don't have to go this elaborate. But when does it make sense? So now we are coming to computational intelligence part of the course for the first time, maybe. And let's see if you like it. So when does expression number 5 beats expression? Let me write here. When does expression number 5, which is I minus n transpose x equal to 0, beats expression A times x equal to 0? Give me a condition. Give me a situation when one is better than the other. Please. Imagine you already have n. Let's not talk about costs of computing SVD. Let's say SVD is already computed when one is better than the other. If your vector is 0 matrix. Very good question. When is 0 matrix? doesn't have to be identity, by the way. It can be any basis in the ambient space. So, but identity is one of them. So when? Okay, let me give you a suggestion. Let's say N is a million by million components matrix. Sounds crazy, right? But in big data, you would have vector matrices like this. In robotics, you would have matrices. Let's say your robot has 50 degrees of freedom. Your state space is 100 elements. So matrices will be 100 by 100. Imagine you do MPC in a classical sense, and somehow you make a matrix of all your steps to the goal. Maybe, I mean, it's hard to say what kind of a matrix you would have. And, it depends on your implementation of MPC. But imagine you basically have A's as blocks in your matrix. And you have, like, let's say, 100 steps. So this multiply dimension of 100 by 100, you have 10,000 by 10,000, something like this. I mean, definitely doesn't sound like a good way to do MPC or anything else in this world, but maybe, you would find that it is a good way. Who knows, right? You do produce huge matrices when you try to solve simultaneous equations. And planning forward for discrete systems kind of looks like simultaneous equations. All right, so imagine A is million by million matrix. I will write here. It will be, okay, let's say 1,000 by 1,000. Okay, I don't want so many zeros. Now imagine null space of A is very small. Let's say it is 2 by 1,000 by 2. Then you can imagine X is also basically a 1,000 in the R1000, right? This multiplication is actually pretty simple. You need to multiply two vectors. It would include this multiplication. Let me write it explicitly. This multiplication would require you to multiply two vectors of the size 1,000 by one vector by of the size 1,000. It would include how many operations? I believe 2,000 operations plus of multiplication and 2,000 of additions. Correct? Or am I wrong? I think so, but around 2,000 multiplications, 2,000 additions. Okay, good. What about this operation? Like this was 2k plus 2k operations. Addition and multiplication should be of the same. I mean, I'm not sure computational complexity, but I think they're of the same order, approximately. They are at least fundamental operations of the processor. Okay, what about this one? What is this? Well, first of all, let's realize what this matrix is. What is this matrix? Or is this vector, sorry? It is vector in R2. Right? Correct? Has to be R2. So this matrix is 1,000 by 2. So it would be, again, what would it be? I'm not sure if there is a way to speed up those kind of computations, but you basically multiply each of those by one number and then by another number. I'm not sure if a processor can speed this up. If it cannot, what you would have is, again, 4,000 operations, I believe. Correct me if I'm wrong, but you understand the order of magnitude, right? So again, 2k plus 2k. I think, correct me if I'm wrong. Maybe I'm incorrect. But okay, now this guy is not an operation. So multiplication, this is not an operation, doesn't require any computations. Now this is 2,000, 1,000 subtractions. Oh, yeah, 1,000 subtractions. So understand what's going on here, right?
The number of operations is, unless I messed it up here, supposed to be
9,000. Now imagine this. How many operations there are?
Well, this matrix A
has million elements, right? So multiplying X by this matrix would require, I believe, every element to be part of at least one multiplication and at least one addition, right? So I would expect 2 million operations. So you can compare the number of operations in both cases. This is, of course, a result of a huge cheat when we managed to get n for free. Getting n would not be very simple, but maybe it would be. I mean, who knows? Maybe you already had your SVD decomposition. Happens all the times that you need it. So in this case, it is much more beneficial to avoid multiplication of matrices. I hope now you see for the first time why it is nice to think about all decompositions of matrices as a source of speed up for your code. Okay. Maybe it sounds to you all as in like, okay, this one case that I'm going to use once in my lifetime and probably not going to use it because I will forget is like benefit so far. But it is not about this case. It's about the way of thinking about it. Like I promise you, I didn't remember this case before I started going through the slide. But you see it automatically when you look at this and say, okay, why the heck do we have this complicated expression where we have such a nice way to do it this way? Okay. Okay. By the way, notice that if you are planning to use this pseudo-inverse, it's not clear if you are going to have any benefits. Because the pseudo-inverse for a long matrix like this, you have to wonder just how costly it's going to be. But transpose, completely different story. Okay, good. Now, going on. This is a slide basically when we discuss exactly the same thing as I put on the paper. Oh, sorry, on the blackboard. So first notice that in the second row, we have ax1 equals to ax2 equals to y. This is the argument that we already had. This is the proof that x1 and x2 cannot be both in the row space because the linear combination is not in the row space. And second, here you have the argument that if x star is a solution, that x star plus xn is also a solution as long as xn is in the null space. So if we have a solution to a linear equation, you can extend it to a family of solution just by adding to it elements from the null space. And you have a, so this x star can be called a particular solution. Particular, not partial. I'm not sure why it is partial there. By the way, the slides are available on the GitHub, and you can correct my mistakes, which are plenty as we see. So, particular solution is any solution that is satisfies original equation. Null space solutions. When we talk about null space itself, like xn, is not a solution at all. But you can add xn to any particular solution to get another particular solution. But you can have the smallest norm particular solution. And the smallest norm particular solution is actually an element of the row space. Why? Because of this argument that we erased on the blackboard, right? Because if there was element of that was not in the row space, that was the smallest particular solution, then we could decompose it into two vectors, one in the row space, one in the null space. And the element in the row space would have to be smaller than the sum of those two for the reason of, orthogonal, sum of two orthogonal vectors have to have a greater norm than any individual one of those two vectors. You understand me, right? Okay, good. So smallest norm solutions to linear equations form the row space. That is, by the way, a third definition that you can give for the row space. I'm not saying that those definitions are very good, by the way. It is not my purpose here. And you go ahead and try to prove that they are maybe incorrect. Like previous definition that the way it was written on the slide here, I think this definition, this one, might be just simply incorrect. As I said, it has to be smallest norm, unique solution. So, go ahead and improve them if you want. This is a very interesting idea. So you can say, what is a row space? A row space is a space of all smallest norm solutions to equations that can be formed with a given matrix. And this connects us to least squares problem. You remember least squares problem? What is least square problem? Let me write it here for you. I mean, we'll go back to least squares soon, today even. But I want you to just get your memory refreshed. You have a problem of finding, if you have equation of this type, least squares problem is to find such x that minimizes ax minus y none. So it is a smallest residual problem. But you would also recognize that in case when the residual is 0, you can have either one solution or a family of solutions. What do you mean by residual, by the way? Residual is ax minus y. Okay, so smallest residual problem means find me small x that delivers as smallest e. Good. But what if e can be 0? If e can be 0, it means that there may be one x that solves the problem. If there exists only one x that solves the problem, it means a is invertible. Why? This is something we can already answer. If it is possible to solve it for exactly, and the solution is only one, then a has to be invertible. Why? There are two ways to argue this, and one of them is with subspaces. One is with introduction to analysis or whatever, like whatever you had in your first grade in college. Yes. But how is that proof that? How does it prove that if there is only one solution, then it has to be invertible? Okay, let me give you as a proof. But like try to give me proofs. I mean, if you think you can, just try it. It would make it much more interactive, I think, because this part of the course is where you can show your muscles. I mean, figuratively. Okay, one way to prove it, first year of college style of proof. If there exists only one and only one solution to this equation, then it means that A is a map that maps us from Rn to Rn. And I realize that this Rn you cannot see on the online, sorry. There is an Rn here, okay? It is one-to-one map if there exists only one solution. It means that for unique x, you have unique y, and for unique y, you have unique x. And one-to-one maps are invertible. But is analysis style argument. Okay, let's do it with subspaces. If there exists a solution that makes it go to 0, it means that, and only one solution. It means that the null space has to be trivial. So it has to have only one element, 0. Why? Because if a null space wasn't trivial, you could add to this solution any element from the null space and you would obtain a different solution. But if null space is trivial, it means that the matrix is invertible. I'm not sure if we proved so far that matrix would be invertible if the null space is trivial. we probably didn't. And I'm not sure if I want to prove it right now, because my favorite way to prove it would make a circular argument here. I would prove it by saying that a trivial null space leads to one-to-one mapping between solutions and inputs, and one-to-one mapping requires a inverse. But then my second argument would fall back to my first argument, which I didn't prove in itself. I just give you a theatrical kind of thingy here. Anyway, you got my way of thinking about it, right? Okay, so so now to reiterate, small row space is a space of smallest norm solutions to this equation with zero residual. Okay, if you have a zero residual solution, all the smallest norm solutions to are forms the row space. And by the way, did you learn analytical solution to a least squares problem? You probably did, but we'll see it in today, I hope. And this solution actually is a row space solution. So you don't need to do any extra work. Like solution to least squares problem that you know gives you a row space element. So it's automatically smallest norm. This seems like it is a least residual solution, but also smallest norm least residual solution if you solve it the way we do. Okay, let's move on. This slide pretty much, okay, let's just go through it. Let's say we have x star, which is a solution to ax equals to y. And we have a particular solution xp. We can find it by simply projecting this x star onto the row space. And this particular solution, I mean, please notice that I put particular solution in the row space. We can have x star is also a particular solution by definition, but we can find the smallest norm particular solution by projecting it like this. Okay. Also, we can find this same particular solution simply by solving this equation number 8, where a plus means a pseudo-inverse. And this pseudo-inverse means solution to this problem. So solution to this problem is called, shorthand notation is a pseudo-inverse. Okay. You probably have seen formula for pseudo-inverse, which I think goes like as follows. Please correct me if I'm wrong, because I don't remember for sure. But it goes like this, I believe. I think that is how it goes. This is the formula for pseudo-inverse, analytical one. We'll see it in the slides in a moment. You don't need to memorize it. The only reason that I think I don't make a mistake here is because this part is supposed to be symmetrical. I do just remember that, how should I put it? Let's say A is what do you call it? Orthonormal. Does it make sense? Orthonormal, right? You remember what it means. Every column of A is orthogonal to a different column, and the length of the columns are 1. Then this guy would have to be equal to identity, right? Makes sense. And inverse of identity is identity. So this is why 1 goes away. In fact, this guy only needed for not orthogonal matrices. Sorry, not normal matrices, not normalized. Why? Because it renormalizes the result. And this guy, for orthonormal matrix, would be the inverse, actually. It would be analytical inverse. Because for orthonormal matrices, you just need to transpose them to get the inverse. So this is how you can think about it. But the position of this guy doesn't follow from this argument, but I'm just giving you like a way to think about it. Okay, good. We'll go back to it in a moment. Now, full family of solutions. And this solution in particular, this x star, which expression number 9, x star And the full family of solutions can be given by expression, with a null space and particular solution. And that is important to know. If you have any solution to your equation, you can express it in this form using your row space solution and using your null space. Okay. This is it for row space, but we'll move directly to the next one. Let us do it this way. We'll take 3-minute break. Please don't leave the classroom. Is it okay? Or do you have to leave the classroom? Can we do a 3-minute break without leaving the classroom? Because otherwise it will be 15-minute break. Can we? Okay, I just want you to breathe out and then we will continue. Okay, and we will go directly into the column space and left null space. Okay, 3 minutes. Okay. So we'll continue now to try to see column space, left null space, and control applications. That is going to be difficult because the first two is like easy. The last one is huge and will require us to use all the knowledge we acquired. Originally, it was planned as a 3-lecture series, but we are planning to do all of it in a lecture and a half. And I'm not sure if this experiment is good, but on the other hand, we are still going through linear algebra content that you already received in your previous education. So maybe it is okay. Okay, good. Now, column space. Column space is space of all outputs that the matrix can produce under all inputs. Okay, that's all. Just space of all outputs. We call it C of A, or in literature we will call it image of A. You can also call it span of A or span of columns of A. I think that's what we discussed last Monday, right? So column space is basically the span of the columns. You remember span is a linear combination of all all linear combinations of a set of vectors, but all of them are the same, have the same meaning. Column space, span, image is the same thing. Okay, good. Now, column space also have an operation in MATLAB or Python or other languages. It is called orth for some reason. Can someone tell me why? If you want to obtain a column space of a matrix, why would you call it orth? There is a very nice kind of like meaningful answer to this question. No? Do you know what orth does as a operation? Okay, now I feel justified to give you this introduction to linear algebra, not because you didn't know something, right? But because orth is so useful. And even if all I teach you is how to use orth and null, is already something. Orth stands for orthonormalization. Okay, we discussed orthonormal matrices so far, right? Or bases. Orth just makes your matrix orthonormal. Do you remember from college something about the Gram-Schmidt procedure? Yes. You remember the name, right? Okay. It's a very memorable name at the very least, right? And it's a very boring procedure if you tried it by hand. Who tried it by hand? Oh, good. You survived, so it's at least that's the case. But it's not very practical to do it by hand, right? Okay, this guy does not do it by hand and does not use Gram-Schmidt procedure at all. It is just SVD, same as null, same as everything you are going to use. It is SVD. Maybe I'll draw for you how exactly it works, but for now, SVD. Okay. Why is this column space? Well, because column space, by definition, you can just take your original matrix and say, this matrix is a basis in the column space. Well, your matrix can have linearly independent columns. Then there wouldn't be a basis in our, in the sense of the word that we like. We can say, well, how about we drop linearly dependent columns? Well, the procedure of dropping them is kind of like similar to procedure of orthonormalization. Because, you know, if you are going to drop something from a matrix, you may as well just normalize and orthogonalize its columns. And as you probably recognize, having orthonormal matrix is much nicer than having just a matrix. Okay, good. So this is why. This is a way to get your column space matrix. Okay. Also, if you want to produce all outputs of the matrix, you can write them this way. If you write them this way, you'll have repeated entries, because it can exist more than one X that produces the same output. So if your matrix has non-trivial null space, this notation on the bottom will not produce you the column space. It will produce your column space with repeated entries, which is not the same thing, right? Imagine you want to generate a database for your machine learning application. Would you really want to have almost all of your data be repeated data? Imagine you have 1 million entries, and only 1,000 of those are unique, and everything else is repeated, because you know, even if you have one-dimensional null space, this dimension is going to suck up a whole lot of your entries, especially if you do grid generation. If you do a random generation, it will probably be not a problem. Or if you do like some other advanced generation procedures, such as, what was the name? Basically, sequences of random numbers that span the space even when it has a null spaces. I'm trying to remember, Sobol sequence, for example. Things like this, like Sobol sequence, would allow you to do the bottom of the slide style of generation of datasets, and you would still have no repeated entries. Grid would not allow you that. So, you know, if you are interested in discussing how do you produce inputs to your operator, so you produce unique outputs, you can look into you know, Randan or Sobol sequences, and now you know how to discuss it. You can discuss it in terms of you know, if we had column space, we won't need anything, but we don't, so we need something. Good. Let's move on. There is a relation between column space and null space, as we just discussed. Every y can be represented as a xr plus a, or as a times xr plus xn, where n is in the null space. And it is true for any element of the null space. Okay, what does it mean? Well, it means that if the null space is k-dimensional, this whole k-dimensional subspace is being mapped to a single point in this operation, operation number 1. This whole subspace is mapped to a single point. Well, that means that the number of the dimension of the output space cannot be the same as dimension of input spaces. So let's say your operator was mapping you from Rn to Rn. Well, if you have k-dimensional null space, it means that k-dimensional subspace is being mapped to a single point. So you cannot expect more than n minus k-dimensional output space, right? This is again one-to-one operator kind of argument, because if you had a output space of more than n minus k dimensions, well, I would ask you, please give me unique input points for every output point, and you wouldn't be able to do it. For any unique output point, you can give me only one unique input point, right? The smallest no, that's what we discussed. So basically what it means is that your column space has to be n minus k dimensional if you have k dimensional null space. It would seem as if they shouldn't be related, null space and column space, but they are. All subspaces are related. Remember in the first lecture you said something about rank, and I think all of you said something about rank, right? We were kind of repeating the word rank all the time. Well, n minus k in this case is a rank of the matrix. So if you have k-dimensional null space, your rank is n minus k. And your column space would have dimensions of n minus k. And your row space would have dimensions a minus k. So rank defines dimensions of the column space and row space. By the way, have you seen operation rank in Python or MATLAB? Do you know what it does? Can you tell me? How? It calls SVD, calculates single values that are non-zero, which accidentally is the dimensionality of the column space and the row space, and it gives it to you the number. When it gives you a null space, what it does is it calculates the rank again, and tells you, it gives you the vectors of single value decomposition, which are beyond this rank. So you have a rank n minus k, and those first columns on the left, they form row space basis. On the right, they form column space basis. The remaining, on the left, they form null space basis, and on the right, left null space. So basically, a rank is just a way to decide which of the vectors in the SVD decomposition belong to column, which to the left null, and on the input space, which are null, which are row space. So this is what rank is. This is why rank, you can always answer any question of, is the matrix invertible, blah, 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 as, rank should be full. Why? Because what you're saying is actually null space is trivial, or column space spans the whole space, whatever. So that's why rank is so important. But rank is actually just a way to slice the matrices into correct bases, into null space bases, row space bases, etc. Good, and all of it is done with SVD. Good. Next, how to project into column space? Well, actually here, I would suggest this way. Previously, I was always talking about, let's find, orthonormal basis, and you already understand how it is, right? If you have orthonormal basis in the, let's say you have a matrix A, right? And you find C as orth of A, you can project onto C as C transpose X, right? So this is how you do it if you have C. But if you don't have C, you can simply do it as expression number 2. Feels very nice, right? Doesn't require any SVD, whatever. No, at least no column orth. Or is it? Can someone tell me what is up here? Is this like nicer, computationally cheaper? Come on, you can answer this question. Expression number 2. Is it nicer than previous projections? Oh, it is not. The answer is it is not, because this plus sign, basically what it does is it calls pseudo-inverse. Usually it is called pinf in all programming languages. Pinf calls SVD, calculates all the bases which we discussed, and just rearranges them. So basically SVD gives you, let me remember, V, S, and U, right, matrices, decomposition. And what it does, it just puts U from back to the front. Don't take it literally what I'm saying. Just it transposes it, brings it to the front, V to the back, and S is being replaced by diagonal where elements are 1 over S. Okay, S is a diagonal matrix of single values. That's what pinf does. So computationally, this is exactly as expensive as what we had before. All projections have the same expense, unless you already have your element pre-computed. And that is the game. We need to look for pre-computed stuff, because computations cannot be gamed. They are pretty much fixed in their, if you want projector, you have to pay for it in terms of computations. Okay, good. How do we justify this? Well, let me just justify it in theatrical manner, but probably be good as a, way to think about it. So what do we do here? we have y, some element that is in the output space of our, hopefully in the output space of our vector. But it's not completely there. There are components that cannot be produced as an output. So what we do first, we solve this problem. Let me write it. We solve this problem. We find x. So to be more exact, we solve this problem. Min over x. Minimize this residual problem. We find x desired, which solves this problem. Okay, x desired will have to be in the row space of A, right? As we discussed. Now we multiply this row space by A, solution by A. So we multiply x star by A, and we produce some u star. Well, u star would now be as close as to y. Sorry, I say y star. Y star will be as close to y as it physically possible, because this x star was the smallest residual solution here. So the residual is exactly the that we will acquire here. Residual, let me write it as ax minus y. It would be actually the smallest one. So, you know, this residual would be, and this residual would be exactly the difference between y star and y. Okay? So this is how the projection works. Basically, it will cut off everything that A cannot produce and to leave everything it can. Good. So this is how the projection works here. Now, let me just say that it isn't limited to column space, to, you know, projectors that don't rely on bases. Look at this projector. This is a projector into row space. Looks different from what we saw before, right? Before we saw projectors to the row space in this form. This was a projector into the row space before. Now I tell you this is a projector to the row space. How? Well, let me justify it in the exact same way. First, what we do is we say, okay, we have x. Let us multiply it by a and get some y. This is just output of this x operator. Of course, if x could have had a null space component, it's going to be completely ignored here because, you know, null space doesn't do anything. Next, let us solve, you know, let us solve this problem. What is this? This is, again, a least residual solution to this equation. But now this equation is going to have zero residual. Why? Well, because this is how we got the y star, right? We got y star by multiplying x by a. So y star has to be in the column space of a. So this is going to have zero residual. But it is also going to be the smallest norm solution. So out of all possible x, this one will get us the x with the smallest norm. So the x will lie in the row space, because as we know, the solution row space is a space of unique solutions with the smallest possible norm. So this is how this guy is justified as a projector. Does it make sense? I mean, maybe it sounds like, you know, we go fast through unknown territory and just not clear why and how and whatnot. But I hope you follow like the leads that I'm trying to give you. And you on your own, go ahead through those slides one more time and try to make sense of it. Actually, this type of argument is very nice. Why? Well, as I said, this is now a row space projector. How do you give me a null space projector then? No, something like this? No? Now imagine, first of all, let me give you 2 reasons why it is nice. First, you will read academic paper and someone will write garbage like this and will say, you know, obviously X is equal to some value, you know, multiplied by this guy. You'll be like, obviously why? Like, how is it obvious? And then but if you know what this is, you would recognize, oh, row space projector. You say, oh, null space projector. So what you're trying to say is obviously X is a null space component of A, represented in the you know, same coordinate space. Okay, maybe it is obvious, I don't know, but at least I know what you're trying to say. This is the first reason. Second reason, imagine you get this guy, but you don't get this guy. You can write your projectors for free. Without SVD decomposition, you cannot obtain this guy from this guy or this guy from this guy. As far as I know, you cannot. Maybe I'm wrong, but you know, this is my intuition, what it says to me. But if you have this guy, you already can do your projection. If you have this guy, you already can do your projection. So sounds very nice to me. Moreover, if you have this guy, you can do all 4 projectors. You can project to any fundamental subspace. Sounds again very interesting. Okay. Huh? Maybe you would have, no, what I mean is you have a pseudo inverse of A. So sometimes previous computations will just give you a pseudo inverse and you can store it and then you can use it for your purposes. And imagine you, for some reason, you don't get access to SVD decomposition, but you have access to pseudo inverse. Not likely, but okay. Now, by the way, if you don't have, if this happens, you actually don't have SVD, but you have pseudo inverse. First, what you should do is to check your code and see if you can actually store SVD decomposition that was done under the hood somewhere to obtain your pseudo inverse, because that's most likely the best way to solve the situation. But maybe, just maybe, you cannot, and then you know. Okay, good. By the way, are we burning? No? It just smells like smoke here. Okay, if someone sees fire, let me know. Let's go next. Left null space. A left null space is everything that is not column space, just orthogonal complement of the column space. It is all vectors that cannot be produced as outputs of A. Again, this definition I don't like it because it's supposed to be the smallest norm vectors that cannot be produced as A, and then it becomes very garbled. So I think the best definition would be left null space is orthogonal complement to the column space. That would be cleanest. Projector to it, as you can see, expression number 4. And that's it. So it's very simple. Remember, we originally had this discussion of how do you find if a vector can or cannot be produced by A as an output? Well, now you can have a test. Let me see if there is a slide about it. No, the test is very simple. You just say if the vector cannot be produced by the matrix, then it better be true that its projection onto the column space of A would equal to B0. So that's how you test. Do you want to test that the vector is in the column space? You can say that its projection onto the left null space is beta B0. Oh, by the way, I think I have writing below that people can see. Sorry. All right. Okay. We go, I think we got through the subspaces. Now, do we have enough time for examples? How much time do we have? It is 5 minutes past 2. 15 minutes. We're not going to go through all examples. We'll go through some of them. But the examples are very important, so I will continue next lecture. Okay, let me start with this example. Have you had control theory? Oh, good. Do you feel very familiar and very strong in control? Kinda, good. That's very good. So imagine you have LTI system of this form. X dot equals to AX plus BU. LTI means linear time invariant system. Basically, you can think about this differential equation. We want to find if there are states that can be made into fixed points. Fixed point is when X dot equal to 0. Okay. So basically, you want to turn it into AX plus BU equal to 0. And what I'm asking is find me such x's that for some u it is possible. And that's the first problem. Let's solve it. State equal x equal to 0 is indeed can be made into fixed point under control. U equals to 0, k minus kx equal to 0. Let me just write. I think it'll be easier if I write. So what I want is find such x star that for some u this is true. So if x star is equal to 0, then what we have is bu equal to 0, and for any u of the form for 0 u this is true, or for u equals to minus kx, which is in this form would be still 0. This will be true. So it is possible to basically stabilize the origin. That is always true. Okay, for this type of systems. Now, second question. Find all states that can be made into fixed point under constant control law. Constant meaning control law has to be equal to some constant, not a linear function of state. Okay. Okay, let's find it. What does it mean? Well, it means that we need to find such u that this is true. Well, we can rewrite this question as follows. A, B multiplied by x u should be equal to 0. That means that we just need to find x and u in the null space of this matrix. So we'll say that all x and u, which can be written as null space of AB times z, where z is just some arbitrary vector. All of those will be solution to our problem. And our problem is actually just the, basically, the solution is defined as a null space of this matrix. If we want to specifically find x, we take first n rows of this matrix, as written on the bottom of the slide. Good. Yes. Now, z is what I'm saying for any z in the Rk, where k is the dimensionality of the null space. So what we are saying is any vector x and y, x and u, that can be obtained as a null space, as a, let me rewrite it this way, okay. N is equal to null space of this guy. Then the solution is all x and u that are n, z, where z is this. So we can find now a basis in this null space, and we can obtain any solution to this problem as now n multiplied by any arbitrary vector. And the dimensionality of this null space, the number of columns in this matrix, is the dimensionality of the answer. Good. Questions? Okay, next. Checking fixed points. Given LTI system, x dot equals to ax plus bu, let's check if x star can be made into a fixed point. And we'll assume under constant control law too. And second, find control constant. Can we make into fixed point? Yeah, and the constant. That's a mistake. It should be can be made into fixed point under control law that is written there. Let me under this control law. Okay. and then find control law constant that does it. Well,
let's try it. First, we know that u equals to minus kx plus u star.
Let's substitute.
We get a minus bk x star plus u bu star equal to 0.
That better be true. How can we check that it is actually possible to find u star such that it works? Your suggestion. This is a subspaces problem, so think about it in terms of subspaces. Well, the way to do it is to say that let's rewrite this equation as such. Let me put minus here. I put equality sign here, right? And this vector better lie in the column space of B. If it lies in the column space of B, we can find u that would solve it, right? How do we check that the vector lies in the column space? Well, we check that it does not lie in, no component of it lies in the left null space. So we check that I minus B pseudo-inverse times A minus BK x star is equal to 0. That's the condition for it to be solvable. Okay. Good. Second question, find control constant that does it. How do we do it? Well, we just look at this equation, we solve it. I mean, that is just a least squares problem, right? How do we solve it? Well, as usual, u star is equal to B minus B pseudo inverse times A minus BK times x star. Why do we even need to look at this condition? Couldn't we solve it just like this? Like, what is the value of checking this?
This will change the control signal.
Hmm?
This will change the control signal, A minus BK.
Would change what?
The control signal that's going to the...
No. The solution doesn't depend on, I mean, this is just, here solution, here check. Why check? Why do we need check? Come.
To make sure B is invertible.
It is not invertible. B is almost never invertible. But you are very close to the correct answer. Well, here's the deal. This, what we try to say is there exists a solution that actually solves this exactly. No residual solution exists. This guy doesn't care if no residual solution exists. It will solve the problem even if there is a residual. It will provide you the smallest residual solution, not zero residual solution. But smallest residual solution has absolutely no value in this context because you're not going to stabilize create a fixed point. You're going to create a different fixed point, not the one that you asked. So what is the, I mean, it's nice, maybe someone will one day ask you, create me any fixed point that you want. Like your robot is supposed to stay here, but will stay here. Maybe it's okay, but maybe it's not, right? Imagine if you want to solder something and your robot stays here. It's like not very nice to solder it here when there is like nothing to solder, right? So makes sense to check if you actually can or cannot create a fixed point that you are required to create. This is the check. And as long as this check tells you that there exists a solution, a zero residual solution, then this guy, least squares, will provide it. That is the power of knowing. If you know that zero residual solution exists, you are free to use your pseudo-inverse and you will get exact solution with no residual. But if you don't, you cannot use your least squares, because what you might get is a solution with a residual, and your following arguments will have to include this possible residual, which is sometimes not acceptable. Understand me, right? Good. So let me check. We have 4 minutes left, so let me just see the next problem. Okay, let's do the I'll do this one problem very fast, and then the following ones we will go through tomorrow. Okay, so last problem. Let's say you have a fixed point xd, sorry, a state xd, and you know it cannot be made into a fixed point. So xd cannot be made into a fixed point. And you want to find a fixed point which is closest to xd, which can be made into a fixed point. That's exactly what we just discussed, right? You cannot stabilize your manipulator here, but you can stabilize it here. So let's just ask for the smallest fixed point you can get. Okay. How do you do it? Well, a very simple argument is as follows. Remember from the previous first example that we had, we said that all fixed points can be expressed as xu equal to n times z for the system. We just found it in the first example. That means that x that can be made into fixed point can be expressed as nx equals to z, where nx, basically where n is equal to nx nu. Does this make sense? I just sliced this matrix like this. Okay, so all solutions have this form. Great. Now I'm asked to find xf, which is the smallest difference from xd, but I know that xf is supposed to be equal to nx times z, something like this. Well, how do we do it? Well, this is a subspace. This xn is a matrix which spans the subspace, right? Like any matrix spans subspace, column space it's called, right? So what we need to find is a projection of this guy onto this subspace. By projection, we said we needed the smallest point, but this is the definition, right? Projection is the point in the subspace to a given vector, which is the closest to it. That was the definition of a projection. So let's just use our knowledge of projectors. What is a projector onto the column space of xn? Please answer. What is a projector onto the column space of xn? Come on. You is this correct? Nx, something like this? No, you want it this way? No, this would be row space. So you would want this way. This would be a column space because you, the way you think about it is you, let me write it this way. You have this vector, you solve the least squares for it to get a row space solution, then you project the row space solution back into the column space. That's how you get it. Okay, not incorrect. Why? Because this matrix is not orthonormal. Why it's not orthonormal? Because orthonormal matrix was this one. This one, its vectors are orthogonal, but not normal. So careful. That is answer. That is answer, and you can see it is very easy. You can see just how easy the argument is. It's mostly words. Like you just have this one operation, which is very easy to get. And you know, you don't even need to see inverse here. If you can normalize the vectors, which is a operation which is not very costly. You know, think about it on your own, how costly it is to normalize a vector. The cost would be not very big, right? would have a lot to do with the cost of the norm, right? And but you can do this inverse, of course. And if you think about it, this is also a problem that is not so trivial, right? I'm just asked you to find the closest point to a given point that you can stabilize, you can make it a fixed point. It's, it's very practical, and you can see just how easily we attacked this problem and solved it. There are enormous amount of problems with a similar nature. We'll see 2 or 3 next lecture, and also next Monday. And after that, we'll go into towards optimization part of the course. So next Monday, a little bit more linear algebra and optimization. Please don't forget this content. It's going to be extremely important throughout the rest of the course. Make sure you use slides or whatever to self-study, because I don't believe that you can just magically switch on linear algebra in your brain. You need to study it. Okay. Right. Good. That's it for the lecture, and we'll see each other on Monday.